nicer. And you have probably seen bar graphs when you were 10 years old. And I'm not going to do anything particularly different. So hopefully this is going to be, the first part is going to be what you see is what you get, right? So we're going to look at two kinds. Bar graphs that use ordinal data and bar graphs that use nominal data. Now, remember those two words were to do with what does the data look like, right? Now, there is a difference between ordinal data and nominal data. Nominal data would be things like, what's your favorite color? And people say, you know, 13 like red, 22 like blue, and 15 like green, right? And this would be called nominal data. This is the lowest level of data. You can't really do much with it apart from count how many people said yes. Secondly, it's nominal because none of these things can be put into any sensible, agreeable order, apart from alphabetic, and alphabetic doesn't count, right? Would you agree that red is no better or darker or nicer or any other word than blue or green? Ordinal data can very often, and it is, also things, right? Not numbers, but things. But the difference in ordinal data is that you can put them in order, right? You can do them from smallest to biggest in some sense, or good to bad, that kind of order. So for instance, you might do people who graduated from high school. How many have an associate's degree? How many have a bachelor's degree? How many have a master's degree? And how many have a doctorate? So suppose you know, I don't know, you went to a particular company, you know, like Microsoft, right? And you found out how many people, you know, you asked people in the place, what's your biggest, highest level of education? You know, and 10 of them said, I got a high school and then I joined the company. 7 of them said this, and 5 of them said that, and 3 of them said that, and 2 of them said that. So in one of the offices in Microsoft, maybe that's the distribution. Now, can you see in this case, there is a kind of natural order. Would you agree? High school, lower level of education, then associate's degree, all the way up to a doctorate. And we call that type of data ordinal. And if you're trying to figure out how to remember which one is which, doesn't ordinal sound like order? Ordinal, I don't know that's how you say it, but it's got ordinal in it. That's how you tell the difference between those two. In both these cases, when you take the table, which is basically just a list of numbers next to each item, you will create what's called a bar graph. And bar graphs have a particular shape to them that you need to follow. So let's take this data first, right? It starts off pretty much the way you would expect it to do. Vertical is your frequency. If I'm doing this data, the biggest number is 10, so I'd probably go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And along the horizontal, you put a label. And then you should typically have a heading, tell people what this data is, and it could be people in a Microsoft office. So you went into one of the many, you know, big offices that Microsoft have over at Microsoft, and you just asked everybody what their highest educational level, and this is the results. And now we're going to put this onto our diagram. So you make a little mark and you put high school and you do a rectangle and you go up 10 high. And then you leave a little gap, a big gap or a little gap. That's, I guess, your choice. No particular reason, I'm just using a different color pen because I want to. You then do associate's degree. And there were 7 of them, so that would be here. And you do another rectangle the same way. You know how this is going to end, don't you? It's just going to be gap, next guy, next guy. So I'm going to be pretty quick here. The next guy is going to be those who had a bachelor's, and there was 5 of them. Another gap, master's degree, there was 3 of them. And then another gap, and then those who got doctorates, and there was 1 of them. Now, just by coincidence, this particular bar graph has a kind of like stairway thing going on, right? That just happens to be coincidence. Isn't it totally okay if these are all different heights? Goes up and down, goes up and down. It is what yes, right? You can look at a diagram like this and you can certainly tell some information visually quite quickly. Aren't there a lot more high school graduates than there are doctors in that office? And you could also sometimes, only sometimes, you can see a trend. There are fewer of each higher, right? So the higher level that you go up, there are a lot fewer people that have that. And that's kind of sensible. See, if you took the area that you lived in and you found the highest educational level that people achieved, there probably should be another column over here, you know, people who didn't finish high school, right? Those who didn't graduate, right? But in this case, everybody had some kind of situation. So you would have that, and you might see a pattern. That wouldn't surprise me, for instance, if I looked at my street and I found out how many people had each of the degrees. We have probably a decrease. And I think it makes sense. You know, you can't get an associate's unless you get a high school degree, right? So going to be less of them typically, right? And only so many of those get that, and only so many of those get that all the way down the food chain, right? There's a lot less people with doctorates than there are people with high school graduation, right? There just are. Are we cool with that general process? Nothing really tricky about it. Don't overthink it. It has its own kind of shape to it. Now, you can take this same chart and you can do this to it. You might want to turn the 0, 5, and 10 round, but this also counts as a bar graph, right? Do you see that the rectangles are going that way? And this fella up here is a frequency. That is fine. I mean, it's just orientation. I've seen bar graphs vertical. Me, personally, I like them vertical. They just look better. But can't you have them side on? And it still counts. I wouldn't normally take a histogram and do that, although I guess you could if you wanted to. You tend to make histograms go vertical. But bar graphs can go 2 different ways. Now, if I did the second one, I wouldn't do a real version of that one, but can you imagine you'd go red, blue, green, and you'd pick some kind of scale, and that would be red, and this would be blue, and that would be green, right? And you'd be done. So spaces are important. If you don't put spaces, it's not a bar chart, right, or a bar graph. Vertical axes makes sense. Sometimes don't you have to change the scale here? One box represents 1 doesn't always work. Can you imagine that was 120, 59, 72, things like that? You might want to choose a different scale like 10, 20, 30, 40 or so on. It's not uncommon for people when they do them to do that. Have you ever seen bar charts where they just stick numbers at the top? It saves you having to read across and trying to say, is that a 2 or is that a 1? Or actually, that is a 1. Is it a 1? Is it a 2? Is it a 3? That kind of issue. So far, so good. Now, you can take a bar graph, which we have here, and do a flavor of it called a relative frequency bar graph. So let's do it with the high school data again, right? So you've got high school and you've got the frequency. And this was 10, and people with associates was 7 of those. Those with the bachelor's degree, 5 of those. Those with the master's degree, there's 3 of those. Oh, I apologize, that's a 1. It's a 1. And those with the doctorate, there was 1 of those. we need one more column, and that's going to be the relative frequency. I'll have to add these up: 17, 20, 2, 3, 4, 5, 26. So this fella here, 10 out of 26, and I'm going to go 10, I'm going to divide it by 26, and the answer I get is 0.38. I'm just going to round it off to do decimal places. And then the next one's going to be 7 divided by 26, which gets me 0.27. The next one's 5 divided by 26, and that's going to get me 0.19. The next one's going to be 3 divided by 26, and that's going to get me 0.12. And the last one's 1 divided by 26, and that's going to get me 0.04. So when you do a relative frequency, you just basically find out what fraction each one is out of the total, in this case 26, and convert that into a decimal. Now, decimals are good. You can also do a flavor of that. And instead of using a fraction or a decimal, can you also use the equivalent percentage? Of the three, I don't like fractions because they're just ugly and they're hard to visualize. I like decimals, at least I think of money when I think of decimals, so it's easy to tell who's big and who's small. My best is I like percentages. I think percentages are just easier on the eye. Now, if you take this guy here and you want to do a bar chart, you go high school, associates, bachelors, masters, and finally doctorate, right? And that's educational level. And here, I'm going to do percentage. I could have done relative frequency, in which case I'd use the decimal numbers, but I'm going to do percentages. And since the biggest one is 40, can you imagine when I go 5, 10, 15, 20, 25, 30, 35, 40. And so 38% would be probably about here. Oops. 27 for the associates is probably somewhere around about here. The bachelors is 5, so that's some, whoops, don't go too high, somewhere about here. The masters, 5? Bachelors is not 5, bachelor is 19. Oops. Next one is 12. And the last one is 4. Can you pretend that I did this really well and I did it in square paper? And if I did it really well, wouldn't these gaps be the same size? Right? The fact that they're not is just because I was rushed in doing it. Now, if you do your data and it's ordinal, or you do your data and it's nominal, the only real difference between what does the bar chart look like is that when it's in ordinals, shouldn't you do from left to right the order? But when it's nominal like this, couldn't you jumble them up and nobody cares? It's a minor difference. But couldn't have done this one blue first, red second, green third, and it wouldn't really change anything significant. But in this case here, I think it truly does make sense that you should put the x-axis in the order that your ordinal data makes most sense in. There we go. Now, are we happy about bar graphs? Can I move on, or is there anything about them that you're not sure about? Because there's not an awful lot you can do. I guess I should have said, you could be asked questions like, what's the most popular, what's the least popular? You know, those kind of questions. And so I could say, High school graduates is the most frequent. Doctorates was the fewest. Red was the most popular colour. Blue was the least popular colour. There's not an awful lot more you can get out of these pictures apart from that, right? Occasionally you might see a trend, but that only is true when you look at ordinal data. So back to my question, do we have any questions? We cool with that? You learnt it when you were 12 or 10 or whatever, and nothing much has changed since then. Maybe a few terms that we use that you're not familiar with. Right. Have I done time series for you yet? Have you seen one? Good. Right. So this is another different kind of graph. The only reason I'm doing this table horizontally is because it uses less room. Some tables go vertical, some go horizontal. No other significance to it, except it takes up less room. So let's do time. And after time, we'll have, say, temperature. And you were doing a little chemistry experiment in this story, and you were watching a chemical reaction, and on this chemical reaction there was a thermometer, maybe a digital one, right? You stick it in and it's got a little screen and you read it. And every minute, you record the temperature. You may be hearing my dog. Come on, let's go. There we go. That was her telling everybody it was time for the poo work. And my wife is taking her out. So in this story, let's make the temperature in centigrade. So it started off at 50 degrees, and then it became 60, and then it became 75, and then it became 89, and then it became 91, and then it went 80 degrees, then it went 70 degrees, and then it went back down to 60. So you can imagine over an 8-minute period, there was some kind of chemical reaction, and now you've got your data and it looks like this. And you might think, how would I like to write this down visually? And the answer would be you're going to do what we call a time series. It gets its name because the variable is measured in some kind of time. This could be, you know, an 8-day period, and this is the highest temperature that you got each day. This could be, you know, 8 times I went out doing my 100 meters, and this would be how many seconds it took me, right? Or whatever it is, right? Different kinds of data that involves time. So to create these guys, you have your pretty basic X and Y axis. Along here, you do time. And in this case, minutes. And vertically, we have temperature. So do you see in this case, neither of those two numbers is a frequency, right? At time 2 minutes, the temperature was 60, right? There are no frequencies involved in this kind of data, right? It's specific time points. So you would say at the 1, the 2, the 3, 4, 5, 6, 7, finally 8. And the biggest number I need is 91. So I can go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So I'm using a scale of what one box represents 10 in this case. How do you think I'm going to represent 1 minute the chemical was 50 degrees? How's that going to appear on this?
With a point?
Yeah. At 1 minute, 50 degrees. At 2 minutes, 60 degrees, which is here. At 3 minutes, it's 75, which I'm guessing is about here. At 4 minutes is 89, which is almost 90, so it's about here. That one's just a little bit above it. That one is on the way down. That one's on the way down. And that one is on the way down. Can you pretend I plotted them accurately? If you have square paper, you do a better job. What do you think I'm going to do with all these dots? I mean, I guess I could leave them, but I'm not.
You connect them.
Yeah. And you're going to just connect them, not very imaginatively. And you now have created a time series. Now, when I look at this table and I look at this picture, for me, because I'm a visual learner, this picture is easier for me to see what's going on than this list of numbers are. For instance, doesn't this particular chemical reaction involve a lot of heat is getting generated, right? Well, for a few minutes, and then doesn't it kind of taper off? You know, that kind of reaction where when you mix two chemicals, it heats up for a little while, but after that, you know, it stops heating up, right? It doesn't get hotter and hotter. It just, you know, levels off, and then, you know, it cools down because of room temperature or whatever. So that's what a time series can look like. Are we cool about that? I mean, if you've never seen one, I don't think it would be difficult for you to create one. You could have been the first person who designed this, right? It's a very simple way of describing data. Are we good? Right. Can I move on from this? No questions? Right. So let's look at another type of graph, right? Another way of visualizing information. And this one is going to be called stem and leaf. And I've already done this with my night class. So I am going to take some data and show you a way of visualizing it. This particular thing's going to be called a stem and leaf. So I'm going to go out and get some participation from you. Oh, before I forget, let's take attendance. So I'll do a screen grab. I tell you, I've noticed something about my screen grabs. Do you know I'm always in class? Oh, come on, that was a good one. Okay, about 5 of you got it. Joshua, did you get that very bad attempt at being humorous? Yeah, you're smiling, okay. So what I'm going to do here, and like all data collection, you are totally allowed to not take part, right? So have we collected data on your ages yet? Remember that one? Okay, so let's collect some different data, but it has numbers on it, right? But it has to have, I need a good mixture for this stem and leaf thing to work. So what shall I look for? I'm trying to find an interesting one that we haven't done yet. Something with numbers in it.
Pets.
You know, oh, they have numbers, but I want things like 20s and 30s and 50s and 70s. And I'm darn if I can think of anything off the top of my head where that's going to work, in which case I may just make up some random digits then, because I've already done your ages. I don't want to do that one again. No, that's a sad one. I won't do that one. No, okay. Since I have no imagination and I can't think of a good question, I collected data from some place, and this data looks like this. 2, 3, 1, 2, 3, 4, 6. So there's 18 numbers here. Now, I can't make a very good frequency table because wouldn't we get a table that's huge and have a lot of zeros in it? I could do a grouped frequency table. And if I did, I might go 0 to 10, 10 to 20, 20 to 30, that kind of thing. But there is another way we can do it. It's called the stem and leaf. So what you do is you draw 2 vertical lines, and we call that the stem. And on the stem you go, what's the biggest number I've got? 80. So you do an 80, a 70, a 60, a 50, a 40, a 30, 20, a 1, and a 0. Now, do you see that person who's 17? And this person that's 21? And this person that's 61? I can represent each one of those people on this diagram. For instance, that 61 gets replaced by that. So the way you read this is that that's 61. Okay, after 61, because I guess I started on 61, what's the next highest 60 after 61?
62.
And so you put a 2 here. And would you agree 67? Looking good? Okay, randomly jumping around. I can see an 81. I think that's the only 80 I've got, so 81. Okay, I can see a 71, so that's definitely going to go there. Let me change that number. Actually, I shouldn't change that number. Okay, 50s. What's the smallest 50 in this list?
55.
Agreed. And then I see a 56. Now, do you notice I have to find them in order, so it takes a little bit of time. 40s are getting really messy. Do I even have a 40? Nope. Do I have a 42, 41? I see a 42 here, and I see another 42 here. I can see a 47. Is there anything else apart from that? No, so we're going to put 47 in. We're going 3 now. The smallest 3 I can see right now is 31. Do you agree? Yeah, so 31 and 31, so that's 31 and 31. Looking around here, I got a 33, so that can go there. I'm looking for 20s now. I just noticed something. Easy fix. Didn't I forget 60? Fixed. Easy to recover, right? Right, keep going now. I'm on 20s. I see a 21. I see a 23. For me, it's a good idea to cross them off as you use them. That way you notice what's left, like that 60. I've got a 17 on its own sum, and then 0, 7, 0, 8, and 0, 9. This is how you construct a stem and leaf. Now, it's a very primitive picture, right? A very primitive graph. It doesn't have a lot of finesse to it, but doesn't it contain the essence of this data?
Mm-hmm.
What you have to do to make it valid is somewhere at the side you have to do a key. And you pick anything you like. You can pick 5/6 means 56 years old. So I'm pretending that this data is the ages of people at a wedding or something, right? And 5/6 means 56. Why do I need that? This same technique could be used if these were 1.7, 2.1, 3.3, 0.7, 6.7, right? You don't know what this represents unless someone gives you a key. It could mean that 5/6 meant 560 or 5,600,000 or whatever, right? If you don't put the key, it's not really complete. Now, when you do these in the homework, you'll get a box a big box, and I'll have a thing that looks like this, and you'll put the, let's put an example, you put the 3 in there, right? And there'll be, and you'll go 1, 1, 3. I've checked this out, and at least it worked on mine. You don't do 1, 1, 3. You don't do 1, hit the space bar, 1, hit the space bar, 3. You go 1, 1, 3. It's very pernickety, right? Now, can you imagine that you made the mistake that I did and you forgot the 6? Can't you go to the row that had 6 on it and just go to the beginning of it and stick in a 0 and everything else gets pushed along and it's fine? So it is easy to fix, right? So that would be the 60s. I guess there'd be a 50 and a 40 in here as well. Are we cool with this diagram? Yeah. Here's something cool about it. Because you always start with the smallest to the biggest. Top is the smallest, bottom is the biggest. If I turn it this way, and I put the New York skyline around it, don't you have a very primitive histogram? So stem and leaf diagrams are very often used as just the rough beginnings of your data, right? You probably wouldn't necessarily publish the stem and leaf. You'd probably convert that into a nicer looking histogram when you're finished. But when you look at this, can you see that in this particular case, there is no rhyme or reason? The data is just up and down like a yo-yo. There is no pattern. And maybe that's it. Maybe there is no pattern. That's what you're finding. Sometimes there are none. Are we cool on that?
Yeah.
Right. So let's do another version called the back to back stem and leaf. Now, to save time, I'm going to pretend there's a whole load of data here. And this is the ages of males in my fictitious statistics class, right? And then I have a whole load of ages of all the females. And I've distinctly separated them into 2 data sets. So what you do is you do your stem and you do the ages. Let's say the ages start at 30 for whatever reason, 40, 50, 60, 70, 80, right? So, excuse me. Let's say that I don't have any, teenagers or 20-year-olds for whatever reason, right? Now, on one side, doesn't matter which one you choose, you put the males, and on the other side, you put the ages of the females. And that's why it's called a back-to-back, right? It's a bit like the spine is the middle, and then everybody back-to-back, right? Now, the males go out this way. Just the normal way, right? The usual way that you would do any stem and leaf. Can you imagine that's just like the one we did over here, right? Now the females, they go this way. If there is nobody who's a 70, you don't put 0 there because that means 70. You put a blank, right? You don't put anything. So there weren't any females who were 70 something, right? That makes sense. Have you noticed that the way the numbers on this side go are from smallest traveling outwards to biggest? On this side, it's the same pattern, smallest to biggest. Now, when you look at this, what it allows you to do is to look at one and compare it to the other. And so you might look at this data and say, What do I notice? I would probably say that the majority of females are in the 30 to 50 age group. On the other hand, would you agree that the males tend to be a bit older, more like the 60s? There's not a lot of difference over here. They're pretty similar. So you can identify patterns and shapes and comparisons between the two. And that's called a back-to-back stimuli. You feel comfortable about how if I gave you some data, you could create that? Right. Now, the homework questions are kind of weird. They're okay. They're not a bad weird. They give you a set of data and you make a back-to-back, but all they do is they give you like 4 or 5 pictures and you pick the right one. You know, that kind of question. Is it A, is it B, is it C, is it D? Right, so that's how they ask this question. And for this type of thing, you know, they do the same kind of thing. Here is some data, which one is it? Now, once you've got the information, especially when it's this one here, can you answer things like, what's the most popular, what's the least popular? Are there any trends or patterns? So what I'm now going to look at, and I don't know if I've done any of this or this is going to be brand new. Have we talked about ways to describe data? Unimodal, bimodal, all that good stuff, right? Yep. And have we talked about skewed left and skewed right and all those kind of things, right? Also, this is going to come out pretty quickly because we've already covered the basics. I'm going to show you some very primitive versions of each of those shapes, and we'll look at how you could answer questions like, what can describe this data, right? So if I gave you a histogram, and it looked like that, right? So this is my histogram. Unimodal, bimodal, multimodal.
Unimodal?
Yeah, one hill, unicycle, one wheel, right? Uni means one, bi means two, multi means more than two, right? So that would be correct. So we would say unimodal. Now, you know, you get those questions, tick all that apply. So there may be more than one thing, right? So unimodal would certainly get its little dot next to it, right? We would pick that. Skewed left, skewed right, symmetric. Or nothing, right? Nothing, you wouldn't put a dot on it, right? Skewed left, skewed right, symmetric. And if you like the word roughly in front of it, do that if it makes you answer the question.
Would it be roughly skewed right?
I would agree. Does that red line help? Right? Visually, you can see it a little bit, right? So, now, unfortunately, that red line is there. So let me pretend that was another little poor guy right at the end. Outlier. Does this have an outlier?
Yes.
So you have a yes, no, or has an outlier, and you choose that. So we're comfortable in how to interpret histograms. Wouldn't this be the same results whether this was individual numbers or intervals, right? So if it was 10 to 20, 20 to 30, it would still be the same unimodal, skewed right, and it has an outlier, right? Very good. Now, it's going to take me a little bit of time to do this, unfortunately, but I want to because it's important. Right, after a lot of work, I built a stem and leaf, right? We can answer those same questions, right? So we've got a stem and leaf here. When they ask you, for instance, is it unimodal or not, you might want to turn it that way. And very crudely, right? Kind of draw the red line, you know, visually it helps, then do it. Unimodal, great. Skewed left, skewed right, roughly symmetric.
Roughly.
Roughly symmetric, right?
Yes.
Does this have anything in the way of an outlier?
No.
No. So do you see that you can actually, from a picture, you can answer those types of basic questions, right? How many, you know, hills has it got? Is it uni, bimodal, that kind of thing? Is it skewed left, right, or symmetric? Or it may have no shape at all, in which case you leave it blank, right? And does it or does it not have outliers? Right now, that's a subjective call, but isn't an outlier typically something that's distinctly different from the rest of the data? Either very big as it is this case, but you could have had an outlier over here as well, right? That would be an outlier, just a very small one, right? I think things are going pretty good right now. Agreed? There's not anything that's been causing you any great heartache. So I want to stop this for a few moments. I can see all your faces now. Are we all happy? Tomoko, are you happy? She's smiling. Joshua, how are you doing? Oh, thumbs up, great man. Right, so let's go and look at some homework questions and see.
I have a question.
Good, what you got?
Is the mound shape the same as symmetric?
When you say a mound shape, do you mean like just one single hill?
Yeah, there was, I forget what homework it was, but there was a question and I chose mound shape symmetric and it was like one hill and I guess I was wrong. I don't know, maybe it wasn't symmetric.
Maybe it wasn't symmetric. I typically don't use that. This
Okay.
book sometimes uses them. I just, symmetric's good enough for me. If you're
Okay.
unimodal and symmetric, do you know you can be bimodal and symmetric?
I think that's what it was and I was
Right.
kind of confused.
Right. Bimodal and symmetric. Can you imagine an M shape where the two hills were the same height? That would be bimodal. There's two hills. But couldn't you split the shape right down the center and the left and right hand piece were roughly the same shape? So it is possible to have symmetry without being unimodal. So it might have been something like that that was going on. Okay. So here we're looking at a very short bar graph, section 2.2. So if you came in late, hold off in doing 2.1. I'm going to be putting a very small video going through. You can just see the answers and you can check them from that. Because 2.1 really wasn't done the way I wanted it to be. 2.2 is fine. So here we have our first question. It is costly and both time consuming money to go to college. Sure is. Does it pay off? You know, am I spending all this money and all this time where I could be working full time? In fact, some of you may be working full time. Good luck to you. That's a lot to juggle, but you may be. But you're probably not working in a high paid job. If you were, you probably wouldn't want to come here unless you've got goals. What's the phrase? A lot of the people I get, for instance, in my night class, are people who work in the shipyard, just because of their schedules, right? So when we took on ground, I had night classes. A lot of them were shipyard workers, and one of the most commonest things I heard from them was, I mean, why are you coming? Because the shipyard pays really good money. I mean, if you work in the shipyard, I don't think there's maybe there's somebody works in the cafeteria. It might not be great money, but for the majority of people, it's very good money. So you're thinking, why do you even need to come to college? And most of them want to. The reasoning is that they don't want to continue to do this job because it's really hard work, and they want to have the managerial job because they know that their boss doesn't do all that anymore. Their boss comes round and tells them to do that job. So they want their boss's job essentially, and the only way they can get their boss's job is through education, right? They get they get an engineering degree typically, right, and then they can be in charge of a unit, and off they go. So education, does tend to improve your wealth, right? You'll make more money, and this is what this is showing you. So according to the Bureau of Census, the answer is yes. The average annual income in thousands of dollars of households headed by a person. I know they're phrasing it some weird way, but this is just government jargon. We're talking about households here. So typically we're talking about adults who are probably got a partner, and one of those two people, not always, because sometimes both partners have an equal paying job, and that's fine, but very often one is making most money and the other's looking after the kids, right? And so they may only have a part-time job. So that's what they're talking about, the household headed by. And that doesn't mean the guy, that could just as easily be a woman, right? And so the best paying person in the house. And here is the numbers. And if you look at them, it goes from 24.7, which is this one, and it finishes to 100.3, which is this one. So someone who has a doctorate will probably be making about $100,000 a year once their career is established. You may have a doctorate and you leave university and you start at the bottom, but you will move up quickly. So when you look at this here, there is 4 bar graphs. You see them? But one set of data. And which one of those 4 is it? And unfortunately, I've left the answer key on, so you see it's this one. But can you tell the heights tell it? Can you see the smallest one is the 20 thing and the 100 and something's over here? And can you also see that this data is ordinal or nominal? I know they didn't ask you, but it would have been a really good question if they had. Is this data 9th high school associates, that one? Is this data nominal or ordinal?
Ordinal.
Correct. You see it's got a natural order from left to right. And when I see this, I can say, yep, you're going to make more money. I only have a master's, so I'm in that level. I wouldn't mind having a doctorate, but I'm too late now, too old. Oh, true story, like sharing family things. I have a huge family, as you know. I have an even huge, if there is such a word, extended family. When my parents, my mum and dad were alive, we decided to have a family get together, right? So everybody, brothers and sisters, it was for my mum and dad's 50th wedding anniversary. And so we got everybody, and at that 50th, and it's increased since then, right? We had all the children. There's 8 of us still alive, so there was 8 of us there. And we had 26 grandchildren, and we had 15 great-grandchildren, and we had 1 great-great-grandchild. And that has increased since then. So if the Robertsons ever have a wedding and everybody comes, can you imagine how many Robertsons are going to be? Well, they're not all Robertsons because my sister get married and their names get changed, but the Robertson clan. And that is kind of cool. And I don't know why I showed you that, but it was cool. I think I'm just getting homesick. And that's the advantage of having big families. When you have a family get together, it's like a town meeting. I mean, it's almost that big. Okay. So can you see that these questions are not difficult? I guess that's also true, right? So here is a story. They give you some numbers. It's one of those pictures. I'm going to take off the answers here because that's just a distraction, right? Here we go. Here is another one. Here is a picture. Now, this is, I think, the only question that they have this thing here. Does anybody know what you call this picture that has circles cut into pieces of pie?
Pie
And they're
graph?
very, yeah. So that's it. It sounded right. Say it again.
Pie graph?
Pie graph, pie chart. Yeah, pie graph. I've heard it called a circle graph. I don't like that name particularly, but it could be called that. One of these four guys is right. It's easy to tell which one of these four, and the reasons it's easy to tell is, can you see you've got the numbers and you just have to figure out which one goes where. And they've been a little bit sneaky. If you look really carefully, do you see they keep shuffling the positions? That's because this data has no order to it. So any order can be done. So you just need to figure out which one matches which. But let's go back to this problem. I'm going to pick Shannon, right? The River Shannon, it's in Ireland. Actually, I've been to Ireland. I've probably crossed that river. It's a big one. I think, if I'm not mistaken, isn't the Shannon the river that goes through Dublin? I believe it is. So anyway, 39, 40.9, 34, 37. This is how you have to find out. The River Shannon had 36 spearheads. This is them just when they clean the river, right? When they dredge the river. Normally when you dredge the river, you're just cleaning up for boats. The kind of things you get are stolen cars that they drove in to get rid of them, right? Old baby prams, things like that. But in these places, because they are so old, when they do that dredging, they also dredge up arrowheads and spearheads from the Bronze Age. And so this is how many have been dredged up, if you're wondering what these numbers. So back to Shannon, 36. If I add that, that's 30, 66, 76, 80, that's 95. So the total number is 95. Shannon is 36. You find out what that is as a percentage. It's 37.9%. And so I look for 37.9%, and that makes it that one. So I'll show you how I did that again. I found the total number of things altogether, there was 95. I found out what 36 out of 95 is as a percentage. I did that by going 36 divided by 39 times 100, and the answer I got, rounded off, was 37.9, and that's why I chose that one. So we cool with that? Apart from that, I think the questions are pretty straightforward. And there is a guy that needs no explanation. Can you see this as an example of one of these, the time series graphs? So here's your data, one of those four. I don't even need to draw that. I mean, I guess I could and then look at my picture and, you know, share it with the four and see which it looks like. Which one of those four is the right answer? And you can tell just by looking at the data.
The second one.
I agree. And I'm pretty sure you mean that one, right? Okay, for those who are nodding, they don't need any explanation. But some of you might be looking and say, how does she know it's that one? It might have been one of the other three, right? So do you want to explain why that's the right answer? What you noticed about it that told you pick the second one?
I noticed that the for the first time period it had the highest number, and the last time period had the lowest number, and there
And
are
it went.
no big changes going up or down in the middle, so it's just going steadily downwards.
I think you said it better than I was going to say it. Yeah, started big, finished small, and everybody went downhill.
Yeah.
Doesn't that look like this, right? Now, can you imagine a different world where it started small, got big, and then went small again? That would probably be picture A, right? If it was picture 4, this one, wouldn't it start small and then get bigger and bigger and bigger and bigger and bigger? So if you're really careful, do you know you can save a lot of time and not actually draw this thing to figure out who the answer is? Right? You can just look at the data and say, yep, you're that one. I hate these things. I'm not going to do it. Good luck. It's not a bad thing. And you just, it's like a pie chart where somebody cut a hole in the middle. I don't think it helps any. It's still hard to tell, isn't it? It is a pie chart with a hole in it, right? That's all I want to do with that one. So let's have a look at checking our time here. Okay. Let's have a look at stem and leaf, because we've, oops, wrong version. You don't want that. Okay. I don't think you can see the stem and leaf right now, can you? Maybe you can. No. Okay. So I'm going to go out and back in, as I typically do. Right. Remember, we created a couple of stem and leaves ourselves, right? So let's see how this one works. In this question here, you physically have to create the stem and leaf. So as you scan through this data, the first thing you need to do is find the smallest and biggest. It'll give you an idea of how to fill in, pardon me, how to fill in the stem. My eyesight is scanning, but my eyesight's not great. I think the smallest is 50 something, would you agree? Is there a 40 anything in there and I just missed it?
This is
I think it's
47.
47.
Okay, I did miss it. There, 40 goes here then. And then what I'm going to do is, then it goes 50, then it goes 60, then it goes 70, then it goes 80, and finally it goes 90. Do you see how that's how you're going to fill it in your homework, right? Now, I have to go back. Let's do the 40s. It would be really helpful if I could put a little red cross through the numbers, but I can't. So I'm just going to have to be really careful as I go through these. So first thing I need to do is, you said there's a 47. Is that the only 40 that's there? Yeah, so all I'll do is put a 7 in there. Now, when you do the 50s, you're not allowed to do this, although it would be great if you were. The first number is 58. The next number is 52, and nobody more 50s. In row 2, no more 50s. When I get to row 3, isn't there a 57? And then there's a 58. Now, do you notice that I didn't put gaps between them? That's actually what you have to do here. But it's still wrong, but for a different reason. When you do stem and leaves, isn't the convention small to big? And do you notice that one of the numbers is really in the wrong place? So I can delete that 8 and put it at the end. And now that I'm thinking about it, do you know that might be the best way to do it? Just row at a time and then fix it later. That way I won't miss one. So that would be my suggestion. If you come up with a better one, go for it. But, you know, that would work. I guess you could print out the page and just cross them off as you did it. That might work as well. And then you go through and you do the last one. So there must be a 91, isn't there? Oh, there's a 90. And there's a 91 and a 91. I can see a 93. No, I can see a 92 and a 93. I think I got all of them, but if I missed one, I guess I'd find out. Now, here's another thing to do. When you've finished this stem and leaf, count all the digits. Let's pretend that there were 27 of them. You look at this data here, and it tells you that there's 32 cowboys. Can you see that if I've only got 27 numbers, I've missed 5, which is horrendously bad. But maybe I'll have 31 numbers, right? And I know there's 32. Do you know, I already know I'm wrong, right? It's kind of hard to do, but don't you have to scan through all the bloody ones to find out the one you missed? I think it's even harder the other side. Do you know if you have 33, you've double counted somebody? Right? And so you have to figure out who you've got 2 of that you should only have 1 of, right? But anyway, you can fix this. The next set of data, I could finish this, but I'm not going to. I'm going to put in pretend answers. Don't pay attention to these particular answers because they're not right. I'm just doing it as fillers, right? Can we pretend that that's what the data looked like when it was finished, right? We can now move on to part B. This particular quote is kind of weird, but Baron von Richthofen. I did check him up because I did it last night. Baron von Richthofen is the Red Baron. You ever heard of him from the First World War? The German fighter pilot? Right, yeah, maybe it's history. Anyway, this guy, when he was alive, went and said this. In his cattle raising on the plains of North America, cowboys are to be found among the sons of the best families. The truth is probably that most of them weren't drunk, gambling lot who were quick on the draw. They were very healthy, hard-working people, essentially. And when you look at this data, which is from 1890, right, which is kind of cowboy time, right, when people were, you know, doing the things. I know they have cowboys today. And you look at the ages of them, the thing that strikes me is look at how many of them made it to the ripe old age of 90-something. And that's back in the days when medicine was not that great. You know, getting a cut and getting it infected could kill you. You know, we didn't have the same antibiotics or anything like that. I mean, they had some home remedies and some pretty violent techniques. You know, if your arm really got really badly infected, didn't they just cut the damn thing off? That was about the only cure. You know, if it got really bad. And it's amazing how long they lived. It's probably a reflection that, although it might have been a hard life in the sense it's a physical life, I don't think a physical life is that bad, you know, because it keeps you fit and you're out of the air. Yeah.
It's good stress on the body, and diet and exercise is really what they say is your longevity really affects it.
Yeah. So what we're reflecting way back in the day. You might, this is me made, I don't know where this data comes from, but I could tell you how I could probably get this data. Couldn't you just find an old graveyard and just go through the graveyard and take the names of males? I'm assuming that in those days, at least, most of the cowboys were boys, were males, and just write down the age, you know, died 97, or they might have said born this year, died that year, and you do a subtraction, right? And you get the data from that. So pretty cool things. And then you choose an answer. Can you imagine making a stem and leaf with this one, and then you type in some choices? And this one looks horrendous, but you're only going to do a stem and leaf for the length of day. So here you take the average length of stay. And when you do the stem and leaf, what do the numbers look like? Well, when you look at this data, do you see that they're all quite small and decimals? So my stem would probably be, what's the smallest number here? Is there a 2 point something anywhere? Takes a while to scan through these. Okay, let's pick a number and see if we can get smaller. Is there anything smaller than a 5 point something? Your eyesight might be better than mine.
5.2 is the
Yeah.
lowest.
Lowest you got, right. So that kind of tells me what I'm going to go here. I'm going to go 5, then I'm going to go 6, then I'm going to go 7, 8, 9, 10, and I'm assuming there's an 11, right? Now, if I wanted to put 6.9 in, right now as a placeholder, wouldn't it go there? If I wanted to put 7.2 as a placeholder, it would go there. And let's just pretend I'm randomly picking in some digits. That's what I ended up with. Wouldn't I then take this and just tweak it a little bit? And now it's done. So I don't know what this data is. You will eventually discover it. Once you've done that, you can then answer questions like this. Now, is it bimodal? Is it skewed left? Is it uniform? And is it skewed right? I think the only term I've not described here is uniform. Uniform is the name we give to it. Can you imagine the data where everybody's about the same amount? You know, like all the rectangles are 5 or 6 high. We call that uniform. you want to stick the word roughly in front of it, you can, but that's what uniform looks like. And this data is going to be that. If I was looking at this data, me personally, I would do some, this is one of my analysis, I would look at that and I'd say Washington, average length of stay. If you go into a hospital in Washington and you're admitted to the hospital, so we're not talking about emergency ward where, you know, they put a couple of stitches and you walk out, right? Not that kind of, but you come in and you're in a bed and you have to be seen by a doctor, right? That kind of physical staying in the hospital, that's where these numbers are coming from. In our state, it's 5.6. Whereas if you go to North Dakota, it's 11.1, which is almost twice that number. Doesn't that kind of make you want to ask questions like, why? Is the quality of medical treatment not as good, so it takes you longer to get better? That's possible. Could it be that the injuries that people get in North Dakota, and we're talking just injuries here, not just illnesses, but injuries, physical injuries, can be quite severe? And therefore, you know, you only need a few people staying 50 days in hospital before they leave to make the average go up quite a bit, right? Like the Bill Gates thing, right? It'd be interesting to look at, because if it's quality of hospitals, then shouldn't North Dakota be doing something about it? If it's something like injuries that are causing long-term hospitals, well, maybe they should be looking about better safety measures. I think North Dakota has, does North Dakota have a lot of oil rigs?
Yeah, a lot of oil fields.
Right, oil fields. You know, there are certain industries that are just more dangerous than others, right? Not many people get hurt working in McDonald's, right? It's a pretty low injury level career. Foresters, right? People who go out in the forest and cut down trees get injured a lot more. And they tend to get injured quite badly when they get injured, right? They're quite severe injuries, back breaks and, you know, serious falls and all that kind of thing. So can you imagine that if some states have got a lot of dangerous industries in them, right? Oil is a dangerous industry, right? There are a lot of things that can hurt you in the oil industry, right? So that might be a reflection of that. Just out of curiosity, what was the 5.2 one? It was Utah? Did anybody get smaller than 5.2? Okay, so let me think, what do I know? I don't know much about Utah. Utah is cowboy country, right? Is it?
I'm not sure if it is anymore.
Yeah. What's Utah got? Has it just got nothing? I mean, it doesn't.
It's more like, yeah, desert land. All my siblings live in Utah, so but yeah, it's kind of just middle of the desert.
So what did people do for a living in Utah? What's the kind of industries you get there?
I think there's a lot of investing in Salt Lake City, a lot of investment firms.
Right, so that's not a dangerous job, right? Typically, not many bankers, you know, lose an arm, right? It's not going to happen that often. So maybe that's just a reflection. Maybe it's a reflection of Utah's medical system is really good. So anyway, I've kind of drifted a bit. When you get good data like that, don't you want to analyze it and think, why is that different from this? And if you are in the government and you're interested in the medical field, isn't this the kind of data that you look over and you talk to people and you go to the bad one and you say, why are you spending twice as many days on average for someone in your hospital than somebody in Washington State, and delve deeper into the data and see if there's anything that can be improved. You always want to improve things. Can you hear, this one is not actually a back-to-back. I guess it was too difficult for the computer to do it. But can you imagine making two different stem and leaves? And that's what's going to go in here. And here's another two different stem and leaves. And here's a stem and leaf. And here's one that's already made for me. And it's a back-to-back. So let's get the context here. This is archaeology. in archaeology, the depth below the surface at which an artifact can be found can be very important. Things lower down tend to be older than things above it. So you can imagine that you find an old city and you start excavating from the top. See the pottery that you come across first, isn't that going to be the newest pottery? And that new might mean 500 years old. And then you go down a little bit further and you get other pottery. Wouldn't that typically be older than the stuff above it? So you might not know the exact age, but you can at least say youngest, middle, oldest, right? And then you can look at other sites and maybe narrow that down a little bit. So yeah, so here we are looking at two sites and they come from similar geographic locations. And notice the stems and the diagram and the leaf and so on. And these are the number of artifacts that were found at particular depths. So a depth of, let's say, 12 centimeters. This site, they found nothing. And on this site, they found, is that the depth? No, yeah, they found nothing. And so this is 12. So what's that going to be? 12 with a 0. Oh, so I misspoke. That 12 and that 0. At 120, they found an artifact, another artifact, another and another. And finally, at 125, they found the last one, right? On this side, by the time you got to 120, there was nothing to find. So you can see that the two sites have distinctly different situations going on. Right. So they've got some cool things and that's good. Let me do it my way. See, when I look at this data here, would you agree that is unimodal, roughly? Don't worry about the little kink. You're always getting little kinks. Do you know if I put one number here or two numbers there, you wouldn't even see it? Right, that's how negligible it is. If you turn your head sideways, could I argue it's roughly symmetric? I'm not sure if I want to call this bimodal or just not give it a name. It definitely isn't symmetric. And it definitely isn't skewed left or skewed right. In fact, it's got a weird distribution. And I'm going to make up a story here. See the site that they were digging, this site number 2? We'll assume that they're digging on the site where a village used to be, right? An ancient village. Do you know this big gap in the middle? Here's a story. Can you imagine a way back, like 2,000 years ago, there was a small village and these are the artifacts. And then they abandoned the village. And then 1,000 years later, a totally different village get built on the same ground. Wouldn't that explain the gap in the middle? Because what you're really looking at is time passing. And time passes, there was some stuff here. And then there was nothing. Because time passes, right? You know, dust builds on top of dust and then, you know, the ground gets taller, right? And floods bring in soil and so on. So that's my made up story for that gap. But can you see an archaeologist might argue the same thing? That on site 2, there was 2 distinct villages that weren't continuously inhabited. Whereas in site 1, wasn't it the same village being inhabited all the time for a long time? You know, every time there was still an artifact. And you could probably even make a guess at what time each village was founded. I'll make numbers up. This village was founded in 100 AD and was continuously inhabited to 500 AD. And then the Romans came and destroyed it, or whatever, right? And this place, right, it was inhabited at that same time. It only lasted for about 50 years and then everybody get killed or left, or a volcano destroyed it like Pompeii, right? And then 400 or 500 years passed and the people said, hey, that's a good place to build a village. Do you know if you go to places that have volcanoes and active volcanoes, like Pompeii, I've been to Pompeii. Do you know Pompeii, there's another city there now? I bet you once Pompeii exploded and killed everybody, nobody wanted to live there in a village or a city format because Isn't it still fresh in your mind? Everybody got killed the last time they had the village there, and that volcano is still there. But you know, after a while, people forget because the volcano never did anything for 400 or 500 years or whatever, and they say, "Oh, let's go back and do it again." Maybe that's a made-up story for here again, right? Kind of cool. You get to do it, and that's the end of that question, and that's the end of that section. Are we cool? So I spent a lot of time going over things, but I think statistics, what I'm trying to teach you is not just, you know, the mechanics, but just ways in which you can look at things and what you might make up. And if you've got a good theory, then it's the next part of your job is to go and get evidence to try and substantiate that theory. And sometimes you go and get evidence and it contradicts what you wanted to be true. And if you're a really good scientist, you live with that. I thought this was evidence that this had happened. But then I go in and look at the history books and blah, 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 and whatever, and I discovered that it had nothing to do with volcanoes exploding, right? It was just the Romans came and killed everybody, which is kind of what happened to a lot of places. And then, you know, nobody liked that place because the Romans had pretty much taken care of it. They killed everybody in sight. And it was only after a long period of time that people, you know, there was enough people and they congregated the back, right? So the fact that there's a big mountain there, a volcano, had nothing to do with the story, right? So you look at the evidence and whatever it tells you, then you follow the data. So we are now going to get a little heads up on your next section, section 3.1. Let me just double check that I've got the right name for it, because I don't know when I call it something. Right. Okay, so I've lost you all. Where the heck are you? Ah, I've lost you. Okay, I'm going to have to stop sharing. There we go, you're back. I have two monitors, so if you wonder why I keep looking around, I'm looking at the other monitor. Because sometimes what happens, it appears on that monitor and not necessarily the one in front of me. So we're going to look at section 3.1, which is measures of center. Okay, let's look at what this story is about. Let's assume that you've collected the data. And we've got good data, right? We've made sure that it was a good sample. We didn't bias it in any way. It was great data. And the second thing is that we've summarized the data graphically, which is kind of what we've just finished doing. You know, you take the data and you make histograms of it, you make bar charts, you make pie charts, you make time series, you make stem-in leaves, you make back-to-back stem-in leaves, right, and so on and so forth, right? And you make frequency tables and things like that as well, right? So that's the data summarized graphically. Now we're going to summarize the data numerically. Now what that means is that we're going to have a set of data and we're going to supply you with special numbers. That are calculated from the data, right? From the sample, we'll call it the sample, right? And these special numbers are called statistics. That's actually where statistics gets its name from. The special numbers that give us some insight into the data. Now, a statistic should be that summarizes the data in some way. The most common ways, there's two very common types of statistics. One is a measure of center, and the second one is a measure of spread. So one number is going to be measuring roughly what the typical person in that data would be, and that's the measure of center. And the second number is going to be a measure of how spread out the data is. Right. So let's show you some examples of measure of center. I'm writing down some data here in order because it makes my life so much simpler. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we have a very simple sample of 10 people. And I would like one number to represent the typical person in this list. And there are 3 versions of the measure of center. We know this fancy term by another name. I'm sure you've all heard the word average. That's really what the measure of center is. It's an average. It's a typical number, the middle kind of number, right, in a set of data. And I said there's 3 kinds, because when you say average, very often you don't really mean that. It's a bad usage of the word. What you probably mean is the word mean. You remember how you do that from way back in the day? To get the mean, don't you add up all the numbers and then you divide by how many numbers there are? Right, so there's 10 numbers here, so you bear with me. 10, 15, 20, 26, 33, 41, 50, 65. And in this case, the mean would be 6.5. And now if you look at the data, would you agree 6.5 is roughly in the middle, isn't it? So if I collected the ages of all of you, I could come up with an answer that the mean was 6.4. Well, that wouldn't be right. 26.4, how about that, right? It would only be 6.4 if it was kindergarten or something, right? So that is the mean. If I gave myself more room, which I didn't, the second measurement is called the median. Now, let's put 3 out the way for a minute. Right, here's my 10 data points again. Now, the median is the middle number when you put them in order. And the median has a little quirk in it. When there's an even number of numbers, in this case there's 10, let's see where the middle is, right? 1, 1, right? 2, 2, 3, 3, 4, 4. Can you see that there are 2 numbers in the middle? The median, any statistic, including the median, has to be a single value. What's the median of 5 and 6 then? How do you think we adapt to the fact that there's 2 numbers in the center?
You just take the mean of the numbers in the middle.
And in this case, the median is 5.5. Now, do you notice that the mean and the median are not the same? There's no reason why they should be the same. Sometimes they are, but more often than not, they are not. Aren't they both trying to tell you the typical person in the middle, right? The typical number in the center of your data. Now, the third one, I am only going to give you a glancing description of it. because virtually nobody uses it, but I'm putting it in for completeness sake. And it's called the mode. And the mode is the most popular answer. Now, in this case here, aren't there 2 5s and there's 2 3s? Agreed? So in this particular case, although some textbooks do what I do and other textbooks don't, I'm going to say that there is none in this particular case. Can you imagine a different set of data where maybe there was 4 5s, right? 4 number 5s, and nobody was as popular as the 5s were, right? Then the median, the mode would be 5, right? Now, you're not going to get too up on the mode because that's probably the one and only time I'm even going to talk about it, because it's not a very useful measurement of the typical person. And can you see that it could be quite random what that number ends up being, even if it exists at all? So far, so good? Right. Now, let's talk a little bit more about the values of some of these, and then I'm going to go back to the mode. We have time, we might. Have you noticed that when you calculate the mean, that the answer you get, in this case 6.5, isn't even one of the numbers in your data set? That's typical. There's no reason it needs to be. What that is saying is that roughly about 6.5 or thereabouts, that's roughly where most of the middle people live, right? Where most of the numbers in the center are. In this case, did you notice that the median also wasn't one of the numbers, right? 5.5 isn't one of the numbers. So that is not a big deal. It does sometimes make people wonder when you use the mean or even the median. Do you know that it depends on which country you're in, but if you're in Scotland, for instance, do you know that the typical number of children a family have is about 2.3 children? Now, can you see how silly that sounds to a lay person? You can't have 2.3 children. See, statistics tells you lies. Well, it's not really. Isn't 2.3 what you get? It's just the mean, right? That's what you came out. Isn't it telling you that it's probably 2 children, maybe 3, right? It's kind of in that ballpark figure. Right? That's the typical person, you know, the typical family in the centre, right? About 2 or 3 kids. That's all it's telling you. And it's okay to have that. Here's a problem which I call the Bill Gates effect. That's just my name for it. You won't find it in a textbook. Can we pretend for a minute that we collected the salaries, or not the salaries, the amount of money, you could call it salaries, that 20 people had that were in a fancy restaurant? And you got the answers. I'm making my life dead easy here. Unrealistic as it is, but it's to get across an idea. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then Bill Gates. There are 10 people in that restaurant. If I asked you to calculate the median, there's not a big deal. Would you agree? 1, 2, 3, 4. It's one of those guys. Hey, they're the same number. 100,000 is what the typical person that was eating in that restaurant, that's their salary. 100,000. Would you agree that's a pretty good representation of that data? In fact, aren't 9 of the people making exactly that number? But can you imagine I tweaked it, I made an 80 here and 120 there, but that would be a fair representation of the typical person. Bad news for the mean. There's 10 people. You put that guy, you put that guy, roughly. Do you know the mean would be 1 billion? Won't his 10 billion, when added to them, they won't make much difference? Won't the total be just a little bit over 10 billion. And if you divide that by 10, don't you come out with an average of 1 billion? Can you see what an outlier can do to the value of an average? And in this case, the mean. The mean is very susceptible to outliers.
In that case, don't you just get rid of the outlier?
That's what you would typically want to do if you wanted to get a better version, a better estimate of what the typical person in that restaurant was, right? So that's the workaround. You would remove the outlier. If you were doing that in an experiment where you did an experiment 10 times and 9 of them were pretty much the same kind of number, but the 10th one was way out, you know, way weird, right? You may have done this. I think they have a phrase, experimental error, right? Don't they say something like that? That one's really just a mistake, right? The machine that was measuring the temperature was wonky at the time, right, or something. And that's how you get around it. If you do government data, if you know anything about me, I don't trust governments anyway, but if you do government data, I do trust their data. I don't trust politicians' interpretation of that data, but I do trust the data. And do you know that when governments do measures of centre, they don't tell you the mean. They always use the median. So they might say the median household income in Washington is $57,000, right? The mean age of someone in Alaska is 47, right? The mean height of this, the mean whatever. They won't use the word mean, they will use the word median, I should say, right? And do you know the reason that the government uses median as a better measurement of the typical centre, the typical person in that state, or whatever it might be they're measuring, is because of the Bill Gates effect. Do you know Bill Gates on his own, divided by whatever it is, how many do we have? Do we have 3 million in Washington state? Is it 5 million? Anybody know?
3 million what?
How many people live in Washington state?
I think 5 million.
Okay, let's call it 5 million. Do you know what Bill Gates and 2 or 3 of his billionaire friends who work at Microsoft and Amazon, do you know those people? Do you know if you took their wealth and added it to how little you make and how, okay, I make, because I'm not poor, right? You put us together. Do you know we're all millionaires? According to the mean. You know, can you imagine what 40 billion would do, or 10 billion? And you know, is it Bezos or Bezos or whatever his name is? I mean, that guy's worth
Jeff
like
Bezos.
He's like worth 100 billion or some ridiculous
He's
number,
now
right?
worth 152 billion. I just
Okay,
saw
since I
a
just
thing on
spoke,
it.
he got another billion, right?
Yeah.
Can
just
you
from the
imagine dividing that
pandemic.
amongst? Yeah, can you imagine dividing that amongst 5 million people? How we could all end up being millionaires? And that's totally unrealistic, right? So if you did the median, you get a much bigger effect, because although these people are really rich, aren't they just one person? And so if you imagine taking the wealth of Washingtonians from people who don't have any money to the Bill Gates of this world, when you narrow it down, won't the person in the middle be the median? So I'm kind of advertising that the median is a better choice if you want to just tell someone the typical person out of a group of people. Right, the typical age, the typical height, the typical wealth. Use the median. If there is no outliers, if you can look at the data and there's nothing weird, the average, which we call the mean, is fine. In fact, there won't be too many differences between the two in those situations. Right, I think we've reached time up, haven't we?